In this video, I have the pleasure to present the Braintool, an anthropomorphic phantom designed to evaluate the accuracy of brain radiotherapy treatments. The phantom was designed by medical physicists of the University of Florence working at the radiotherapy unit of the Careggi Hospital of Florence. The phantom was designed to check the accuracy of brain radiotherapy treatments in a realistic situation. The accuracy is extremely important in stereotactic treatments and in radiosurgery that are delivered to the patient in few fractions with high doses. Phantom design started by generating a synthetic MRI study of a human brain that we can see here in this picture. The study was segmented using simple threshold tools from the MIM Maestro software contouring environment. In this way, the contours of the white and gray matter, of the ventricles and of the skull were obtained. Using the same software, the contours were simplified and then transformed into printable models with the free 3D slicer software. Here we can see the models for the white matter, the ventricles and the skull. The three models were printed through fused deposition printing process with polylactic acid. The printed parts were assembled together to create 4 sealed compartments. 8 plastic spheres were glued into the phantom to create markers visible both in CT and MR images. The 4 compartments were then filled to create realistic CT and MRI contrasts. Materials used are gypsum for the skull, beeswax for the ventricles, and solutions with different concentrations of nickel chloride for white and gray matter. A silicone cover was realized through negative 3D printing. The cover, in addition to simulating the soft tissues above the skull, serves to smooth the corners and create a continuous path for the radiation entry from the apex of the head. Here we can see the phantom realized. On the left, we can see the compartments, the markers in yellow, and the holes that serve to fill the phantom and to host the radiation detectors. On the right, we can see the phantom with the silicone cover mounted. And now I show an example of use of the Braintool to test the accuracy of our gamma knife system. Here, a planning CT scan and a diagnostic MRI are rigidly registered. The differences between the positions of the markers in the MR and CT studies give us a measure of the registration accuracy. To measure targeting accuracy, it is necessary to compare the actual position of the ionization chamber and the position determined in the planning images. A scanning iterative procedure has been adopted for this purpose. Several 4 mm shots were used to deliver those along a linear path in the 3 directions centered around a theoretical position. The charge was collected with the ionization chamber, and the Gaussian fit was performed to determine the position of the maximum along all directions. All scans were repeated around the new positions until the differences between old and new positions were lower than the uncertainty on the planned target position. The difference between measured and theoretical position of the ionization chamber in the planning image set corresponds to the targeting accuracy of our procedure. We can conclude that the Braintool is a custom and easy-to-make phantom. Its anthropomorphic characteristics allow to evaluate the registration and the targeting accuracies of brain radiosurgery treatments in a realistic framework.